Hello everyone, and welcome to a general overview of Deadlock as it applies to Red Hat Linux. Here's an agenda of the topics that I'll be covering. We'll begin with a very brief overview of Red Hat Enterprise Linux, often abbreviated RHEL. Then we'll discuss the four conditions for deadlock, which are mutual exclusion, resource holding, no preemption, and circular wait, and specifically how they're handled by Red Hat. Finally, we'll look into some of the methods employed by the operating system to deal with deadlock prevention, avoidance, detection, and recovery. So without further ado, let's dive in. Red Hat Linux was first released in 1994 and was well received at the time. Versions continued to be released until 2004 when it was discontinued. The OS targeted enterprise customers and offered a lot of customization options, even in way of overall operating system design and deadlock handling. One of the implementation options that we'll be discussing is real-time RHEL. Real-time implies that the machines that make use of the OS perform time-critical functions and have deadlines that must be met, such as those required by high-powered computing environments and server applications. To meet these deadlines, both hard and soft, real-time RHEL employs algorithms that are optimized for maximum throughput, meaning that they try to process as much data in as little amount of time as possible. They also impose much more rigid deadlock handling mechanisms on processes than standard Red Hat does. Another important component in all of this that should be mentioned here is the Red Hat JBoss middleware application, which controls a lot of the locking and deadlock detection mechanisms that we'll be discussing. This is a built-in application on the OS. We'll begin our deadlock discussion by talking about mutual exclusion, which is imposed on the OS through what they call entity bean locks and mutex semaphores. Entity bean locks are traditional software process locks and often lead to busy waiting conditions as one process waits for another to release the resources that it needs. This is sometimes inefficient. Real-time RHEL converts these spin locks into sleepable mutex locks, which sleep processes until their resources are available to be used. Futex semaphores are fast user space mutual exclusion variables, and they're tools that allow threads to claim a mutex without mandating a context switch, which saves a lot of time in these real-time deadline-based systems. Resources are allocated and processes are managed using a fixed priority scheduling algorithm, which assigns a priority from 1 to 99 to each inbound process. Processes that enter with the same priority can be handled according to an algorithm of the developer's choosing. Red Hat system will preempt low priority processes that are holding resources at very specific non-critical points in their execution to make way for higher priority ones to run, although this is somewhat rare and resource holding can often be an issue with standard Red Hat. Real-time Red Hat, by way of contrast, is fully preemptible and makes much more frequent use of CPU interrupts, which allow it to avoid some of the priority inversion problems that standard Red Hat faces. Priority inversion is the name given to the scenario just described, where a low priority task holds a resource that a higher priority one needs. Red Hat deals with both bounded priority inversion, where the low priority task's time with the resource is limited, and unbounded priority inversion, where hold and wait allocation occurs. By way of contrast, again, real-time RHEL only faces problems with the former, the bounded priority inversion, thanks to fine-grained locking control and much stronger preemption. Circular wait is handled by JBoss. JBoss uses an internal global graph of all waiting processes to foresee circular wait and deadlock and take the correct action once it is detected, also to prevent it in some instances. Red Hat, to the best of my research, does make use of some form of the banker's algorithm to allocate resources and keep the system in a safe state, but the extent to which it's employed, given the OS's heavy emphasis on priority processing, is wholly unclear and undocumented. No references to a resource request algorithm were readily available beyond that of priority processing. If deadlock is detected or considered impending by JBoss, as was previously mentioned, it will throw an application deadlock exception, which can be caught and customized by the developer to perform some specific function. But by default, it will roll back all processes that are directly involved in the deadlock, assuming that their priority and critical state are not a huge factor at this point, and it will allow all locks that are pertinent to be released so that all processes can hopefully resume their action without any further deadlock consequences.